Evet, hoş geldiniz hepiniz. Let's start. So last time, what we have done, let me remind you. We defined we proved Hölder's and Minkowski inequalities, right? This is Minkowski, and yeah, this is Hölder's. Okay, let me so. Okay, this is Hölder's inequality. And this is Minkowski. And using this, we proved this corollary that if we have finitely many metric spaces, then on the Cartesian product, we may define several metrics like this for any P. These are all metrics. We proved this. We used mainly Minkowski inequality to show that these metrics are these metrics satisfy the triangle inequality. And we already proved that all these metrics together with D1 and D infinity are all equivalent. We proved this some time ago. And I will finish this section by the following proposition that if, let's say, x1 d1 up to xk dk are complete metric spaces, then the metric space, the Cartesian product metric space x d, where x is the Cartesian product of the spaces, k of them, and d is just d rho. Rho is any positive integer. Okay, so d is any positive not integer, real number or infinite. Okay, are all complete. Since these metrics are equivalent, if one of them is complete, then all of them are complete, because the way you measure things are almost the same. One of them is a multiple of the other metric. So the epsilon delta definitions, which is satisfied by one of them, will be satisfied by all of them. Okay. Therefore, it is enough to prove that only for one of them this product is complete. And we will just do this for k equals 2. First, let's prove this for k equals 2. And for d1, what is d1? D1 is this. So I have this situation. X is x1 times x2, and D1 of, let's say, x1, x2, and y1, y2. So I have the Cartesian product of two metrics, and the D1 metric, remember what was this? So it is just, sorry, uh, okay, uh, all right, I said D1 here. Let me, okay, yeah, the notation is not good because I will use D1 here already, D1 x1 x2 plus D2 x2 y2. So maybe I should okay, let me use D tilde here, and D tilde is this. Okay, now why this metric is complete? Y2, sorry, Y1, Y2. Okay, let's see. So you hear me, but I am not sure whether I hear you because I didn't get any feedback. All right. Now, how can we show that this is complete? So we must prove x d1 tilde is complete. Since all these metrics are complete, it is enough to show that d1 is complete, okay? So I need to take a Cauchy sequence. Take a Cauchy sequence. Well, let's say Zn in X. So Zn is what? Zn is tuples, so it is like this, Xn, Yn. And this is the Cauchy sequence, means what? Right? And this is a Cauchy sequence. Is a Cauchy sequence implies what? Implies that for any epsilon positive, there is some and zero, so that n greater than n zero implies d1 x1 sorry, xn yn m and n larger than, and xm ym is less than epsilon. But what is this? This thing is just, so what is the definition of this? This is the definition of xn xm plus yn ym is less than epsilon, and hence both of them are less than epsilon. And provided that m and n larger than n0. But you see what we have obtained. We obtained the following. Whenever we are given an epsilon, there is some n0, so that if m n are larger than n0, this thing is less than epsilon and this thing is less than epsilon. This means that both of these sequences are Cauchy. Hence, xn is Cauchy in x1 d1 and yn is Cauchy in x2 d2. Well, these metric spaces are complete, therefore these Cauchy sequences must be convergent. Since xi di is complete, uh, both sequences are convergent. Say limit xn is equal to, let's say, x0 and limit yn is equal to y0 for some x0 in x1 and y0 in x2. Well, then our aim is to show that the Cartesian product is Cauchy. So I have to show that the sequence Zn is convergent. But Zn is the sequence xn yn. So we claim that Zn xn yn is Cauchy. How can we prove this? Well, both components are convergent, so this should be convergent. Let's see the proof. Let epsilon be given, then epsilon over 2 is also positive, and since these limits exist, since limit xn is equal to x0 and limit yn is equal to y0, there are positive integers n1 and 2, so that n1 larger than n0 implies in the D1 metric the distance between x0 and xn is less than epsilon over 2, and n2 larger than, not n0, n1, n2, d1, not d1, d2 of yn y0 is less than epsilon over 2. So let n0 to be the maximum of n1 and n2, then if n larger than n0, then the distance between what? Zn and z0. What is this? So this is the distance between xn yn and z0 is this x0 y0. But by definition, this distance is just d1 of xn x0 plus d2 yn y0, and n larger than n0 implies n is larger than n1. But if this is the case, then this first term is less than epsilon over 2, and if I should say n larger than, if n is larger than n0, then n is larger than n2, and if n is larger than n1, then I have that this second term is less than epsilon over 2, so this is what we get. So we proved what? we proved that if epsilon is a positive number, then there is some integer, and if n is larger than that integer, this distance is less than epsilon. And this finishes the proof. Okay. Hence, x1, okay, x1, x2 with is complete. Actually, not only this, since the row tildes are all equivalent, x1 cross x2 with d row tilde are all complete. This is the product of two metric spaces. What about several of them? Finally, you can just repeat this by induction. X1 up to xk and d row tilde is complete. Okay. So all these metric spaces will be complete. In particular, so as a corollary, we have this Rn with d row is complete. Why is that? Proof. Well, we know that R with absolute value is complete. And we just let then what is the row of two vectors? So the row, let's say x1 up to xn, y1 up to yn. This is just summation of xi, yi to the power row I from 1 to n, and then 1 over row to power, right? This is complete. Okay. Hence, Rn, the row is complete by the previous theorem proposition. Okay. Do you have any questions so far? Okay. Yeah, we started with this proposition. Last time we showed that all these metrics d1, d2, d row, right, and d infinity, including d infinity, were all equivalent. And then we showed that if we have a Cartesian product of complete metric spaces, finitely many of them, then the Cartesian product is complete with any of the equivalent metrics. Okay. All right. So that's one thing. Now, finally, we will consider completion of a metric space. Completion of a metric space. Remember that R is complete, right? But Q is not complete, and R is obtained from Q by some procedure. Maybe you have seen this in some other course, I am not sure, but we may think of real numbers as just kind of sequences in rational numbers, right? Any real number has a decimal expansion. Therefore, we may regard real numbers as sequences of rational numbers, and this is one way of obtaining real numbers from rational numbers. And we know that R is complete and contains Q as a dense subset. Therefore, R is a completion of Q in that sense, right? It is a complete metric space and it contains Q as an isometric copy, and Q is dense in R. It turns out that this method works for any actually metric space, okay? If you are given a metric space, if it is not complete, then you can just repeat what you do for rational numbers and obtain a metric space which is complete and it contains the original metric space as a dense subset. And we call that metric space a completion. I'll state that result now. And the book suggests two proofs for that. One of them is actually it's kind of long, the one I just described using sequences. I don't have time for that, and there's another one which is shorter, a shortcut. I'll give that proof. So okay, here is the theorem. Let xt be a metric space. Metric space. Then there is a complete metric space. Complete metric space. X tilde d tilde and an isometry J from xd into x tilde y tilde, so that so this is an isometry. It means that this J embeds xd into x tilde y tilde. In other words, x tilde y tilde contains a copy of this, like real numbers contains rational numbers, so that this is a dense subset of x tilde. In other words, the closure of this is just x tilde. Okay. Moreover, x tilde y tilde is unique up to isometry. Uh, this means what? If you have two completions for x, so if there are two metric spaces which contains x, and if these are both complete and the closure of x in those metric spaces are equal to the whole metric space, then these two metric spaces are isometric. So this means what? Essentially, there is a unique completion of a metric space. In other words, if we think of this in case of real numbers and rational numbers, if you start with rational numbers and if you build a number system or metric space which contains rational numbers, and if that metric space you constructed is complete and contains rational numbers as a dense subset, then that metric space is nothing but the real number metric space, the metric space of real numbers equipped with the absolute value metric. Okay, so that's the content of this theorem. Uh, More precisely, let me write this precisely. If, let's say, x1 tilde d1 and x2 tilde d2 are two complete metric spaces, and j1 from xd into x1 tilde d tilde and xj2 from xd into x2 tilde d1, so this d1 d2 are isometries, isometric embeddings with, so the image of x, and when you take completion you get just xi tilde for I1 2, then these metric spaces are uh, essentially the same. Then there are isometries theta 1 from x1 tilde x2 tilde and theta 2 from the other way around. So that the diagram below commutes. So what does this mean? We have this. So here I have xd, and then there is this embedding j1 to x1 tilde d1, and then there is this embedding j2 into x2 x d2, and there is theta 1 here and theta 2 here, and this diagram is commutative. So whenever you go from x to x1 and then come back to x2 by theta 1, it is the same thing as going from x to x2 via j2. So I have j1 and then theta 1, this is j2, and theta 2 j2 is j1. Okay, and these are inverse of each other. So I have this theta 1 composition theta 2. This is just, if I go with theta 2 first and then come back with theta 1, this is the identity map of x2 tilde, and this is the identity map of x1 tilde. Okay, so this means what? Essentially, if you start with rational numbers and if you want to get a complete metric space which contains rational numbers as a dense subset, you will get real numbers with absolute value metric but no other metric space. Okay, all right. So remark is this: do you have any questions so far? Any questions so far? Okay, remark is the following: the book uh, suggests two proofs for this. Uh, one of them mimics the construction of real numbers from rationals via Cauchy sequences, via rational, via Cauchy sequences, Cauchy sequences in real in rationals. This is a kind of constructive approach, but it is very long. Uh, it is basically this. Okay, so let me just here describe. You have, let's say, rational numbers with absolute value metric. How can we construct real numbers? Well, uh, what we know about real numbers is that real numbers are just kind of limits of rational sequences, right? Every real number is the limit of a sequence in rational numbers. But we cannot just define real numbers as the limits of rational numbers, because, you know, when you say limit, you already assume that it exists, but you have just rational numbers, nothing else. So that's not a good way. Instead, you do the following. We know that any convergent sequence is Cauchy. So instead of convergent rational sequences, I will just consider uh, Cauchy sequences in Q. And I keep in mind that any Cauchy sequence is convergent. But at the beginning, I don't have real numbers, so I don't know whether these are convergent or not, and I actually don't need that. So uh, we just let R as the set of all Cauchy sequences in Q up to n equivalence. Namely this: if I have, let's say, two sequences, let's say these are Cauchy sequences in Q, then we say that they are equivalent. Equivalent. Uh, I will call them equivalent if and only if and only if the distance between them is 0. So limit xn yn, okay, I should say xn minus yn is 0. Okay, so this this is a smart way of saying that they converge to the same real number. I don't mention any real number, but this definition tells me that actually they converge to the same real number. So I don't mention any real numbers, but I actually uh, uh, construct real numbers. So these will be called equivalent if the difference has limit 0. And then what we do next, we define, let's say, the set, let's say, okay, completion of Q. Okay, let me write it. Okay, we consider the set of equivalence classes of these sequences. So I consider all Cauchy sequences. Okay, let me write like this. Xn is equivalence classes. Let me write it this way, of this relation. So this means what? This means all Cauchy sequences in Q, so that their limits are the same. So this is the set of all Cauchy sequences. This is Cauchy in Q absolute value, and limit of xn yn is 0. Okay, so I just consider all the Cauchy sequences in Q so that this condition is satisfied. Okay, and this equivalence class, so it represents millions of sequences. These equivalence classes themselves constitute a set, and you can actually put a metric on this and so on. So let's say X is the set of all these equivalence classes, is Cauchy in Q, and we put a metric on this. One can put a metric on X as follows. So how would you take the distance between two equivalence classes? Well, what you do, you just look at the limit of xn and yn. Okay, of course you have to prove that this is well defined and so on, because this is not just a single Cauchy sequence. It consists of many Cauchy sequences. So you have to show that this limit exists. In case of rational numbers, this corresponds to what? Any real number, let's say root 2, is the limit of a sequence in rationals, like this one, 1, 2, 1, something. But you can write root 2 as the limit of some other So this is limit of some Rn's. I can write this limit of some Sn's, right? One can consider another sequence, and root 3 is limit of, let's say, another sequence Tn, and distance between root 2 and root 3 is defined to be what? Limit of Rn minus Tn, or limit of Sn minus Tn. It doesn't matter which one you choose because they all converge to root 2. So the basic idea is this. And finally, you show that this metric space with D is a completion of Q with absolute value metric. Okay. This is one idea. There is another proof. I'll consider that one. It is shorter. So instead, we will use another approach to construct the completion. I say the completion because essentially there is a unique completion of a given metric space. Let's see how we will do it. Okay. Yani o ispatı vermedim tabii. I didn't give the proof. First of all, you have to embed Q into R. Yani Q'yu R'nin içinde görmeniz lazım. R'yi burada nasıl görüyoruz? Cauchy dizilerinin denklik sınıfları. Rasyonel sayıları şöyle görebilirsiniz. Herhangi bir rasyonel sayı verildiğinde onu constant sequence olarak düşünebilirim. Mesela 3 rasyonel sayısına karşılık gelen dizi nedir? Constant 3 dizisi. 3, 3, 3, 3 diye giden dizi. Bu rasyonel sayıları bu metric space'in içine gömüyor. Ondan sonra işte şeyi de gösteriyorsunuz. Hani rasyonel sayıları constant diziler olarak ben x'in içine koyarsam o dense subset veriyor. Ayrıca da işte bir de tabii şeyi ispat etmeniz lazım. X'in kendisi de complete. Kitap bunu bayağı detaylı yapıyor ama dediğim gibi yani ispatın çok adımı var. O yüzden ben onu yapmayacağım çünkü zamanım yok. Yani ona bir hafta gider. Onun yerine kestirme bir yol var. Bounded function'ları kullanarak onu vermeyi planlıyorum. Cevap verebildim mi? Tamam. Ben de teşekkür ederim. Yani bu sayede beni duyduğunuzu anlamış oldum. Şimdi yani kitapta var. The details of this proof is included in the book, so you can read it. And I'll do the alternative proof again from the book. So idea is this. Idea. Given the metric space xt, try to embed xt into the complete metric space, of bounded functions so bounded functions with the supremum metric. We know that for any set, the metric space of bounded functions on that set with the supremum metric is a complete metric space. So if I can find an embedding, in other words, if I can regard X as a subset of this, then I can take its closure in this complete metric space. Its closure will be, of course, a closed subset of this. But since Bx is complete, its closed subsets are complete. Therefore, the closure of this will be a complete metric space. And that will be my completion. Okay, so you automatically obtain a complete metric space which contains your initial vectors metric space as a dense subset. That's the idea. Is this understood? So uh, we will uh, we will construct an isometry x from x into bx. Let's say bakayım onun ismi var mı? J. Evet. J isometry. Then we will let x tilde. Okay. So then the image will be a subspace of this, and if I take its closure in this metric space is a closed subset of the complete metric space of Bx with the supremum metric, and thus it will be and thus this thing will be complete. It will complete. And so this will be my completion, and clearly it contains a copy of X as a dense subset because it is defined to be the closure of X, basically. Okay. We'll also complete, and so and this will, finish the proof, basically. All right, let me stop here